In this video, I'm going to go through an example where I'm trying to find the expected value of x, and I've been given a joint probability distribution function. All right, so this example, the reason why I chose this example is to help us be able to solve 4.15 or 4.15 in our homework. Okay, so this is kind of similar to that type of question. Their support is different than this one. The support for that, actually it's like a circle, right, with radius a, right? So in this we're going to see that this is actually like a parallelogram. And so let's go ahead and first thing that you're going to want to do for both this question and for 4.15 is graph your support. Okay, so the point is right now we're finding the expected value of x, or mu of x. Okay, so what our goal is the same. The function is slightly different. Okay, but they're equally as difficult. This one is equally as difficult as the one that you're seeing on your homework. Okay, so first thing you want to start with is finding your support. Okay, when I say find your support or graph your support, what I'm saying is graph the values of the function so that with the values of x and y, so that the function, the PDF, is not 0. Okay, so basically graph this area over here. Okay, since it's x and y, you have a two-dimensional plane. Okay, so let's go ahead and graph this. This is x and this is y. Oops, sorry. This is y, and this is x. Okay, so starting with x is between 0 and 1. So here's x equals 0. Actually, let me extend this down a little bit more. X equals 0 is here. X equals 1. Let's go ahead and put that here. Okay, so x is between these two, right? Then we have 0 is greater than, or 0 is less than x plus y. Okay, usually when we graph lines, we solve for y. So let's go ahead and solve for y by subtracting x from both sides. So we end up getting negative x is less than y. So let's see, if I were to graph y equals negative x, that goes through the origin. And let's see, when y is negative 1, then x would be positive 1. So it looks like this. Okay? So this is y equals negative x. Okay, y is greater than that, so that means I should be, when I'm shading, I should shade it above this in the y direction. Okay? And then let's go ahead and the last piece is x plus y is less than or equal to 1. Okay, go ahead and subtract x from both sides. 1 minus x. Okay, let's go ahead and graph y equals 1 minus x. So that means it has the y-intercept of 1. Negative 1 is the slope, right? And solid line, since it has that equal. Okay, that's supposed to be a straight linear line, right? Okay, and so this line that I just drew, this is y equals 1 minus x. Okay, so y is less than that line, which means I should be going downwards from there. Okay, if you put this one, those 4 lines, and you put the information that we have about the where x and y should be, if you put all that together, you get that this is the region for the support. Okay, so you see that parallelogram shape that I said that you should have for this one. All right, so in your homework, you should get a circle. Your shape should look like a circle, right? But it's a very similar type of question. Okay, so this is my support. So now that will help me enormously when I'm trying to find my integration bounds, when I'm trying to find the expected value of x. Okay, so now how do I find the expected value of x? By definition, the expected value of x, if you integrate the marginal distribution, I'm going to use f, but I'm going to use the subnotation of x to note that this is the marginal distribution of x. Okay. By definition, this is what the expected value of x is. Okay. So let me go ahead and I'm going to actually use that notation up here. Instead of calling this f, I'm going to call this the joint distribution fxy. Okay, so that makes this f different than the marginal distribution f. All right, so what is this f? What is the marginal distribution? What's the definition of that? This is the integral from negative infinity to infinity of the joint distribution, and I've integrated out y. Okay, so actually I could plug this in there, right? So let me go ahead and do that. The expected value of x, or mu, right? Same thing as the mu of x. This is, first thing I'm going to do, I'm going to write my integration. I have my x, I'm going to write the dx, right? So now I'm going to plug in this for the marginal distribution of x. So the integral from negative infinity to x, f of x, y, dx dy. Okay, dy. All right, so these guys are the same. All right, so now using properties of integrals, this x, it could be in here or out there. It doesn't matter because this inner piece is integrating with regards to y, so that x is just like it's a constant. Okay, so I'm going to bring it in. All right, it doesn't matter, but I'm going to bring it in because I'm building up to something here. All right. All right. Now, the question on the discussion board asked, what's the deal? Sometimes you see it written dy dx, and sometimes you see this written dx dy. All right. So by definition, this is the expected value of x. I've written it here, right? By definition, right? I've combined two different definitions, but basically this is the expected value of x when you have a joint distribution xy. So what's the deal? Sometimes you see it dx dy. Well, dx dy, it doesn't matter. A general property of integration is that you can integrate a function dy dx, and you can integrate it dx dy. As long as your bounds are matching whatever integral you're doing, they're the same thing. So using properties of integrals, this, what we've written here, is exactly the same thing if I had written it this way. Okay, it's exactly the same thing had I written it dx dy. Okay, now it's really important if you write a dx dy that you brought in this x from the outside, because now when you're doing this inside integration, that x needs to be here. Okay, all right, so by properties of integration, these two are the same thing. Okay, and you can go ahead and solve it both ways to convince yourself. Sometimes doing it one way is easier than doing it the other way. Okay, and actually that's what we're going to see when we have this parallelogram shaped support. One of these is easier than the other. All right, so actually let's go ahead and set it up for both, and then we'll solve it for one of them. Okay, so I'll go ahead and set it up for the easiest way to do this first. Okay, so this expected value, if I'm trying to find this expected value, all right, so I'm going to do my double integration. What is it easier to integrate over first? Well, for this support, if I integrate over y first, so then I would basically be going from this line to that line. Okay, and then I integrate over x, so then I would integrate over x from the entire, from 0 to 1. Right, 0 to 1, right? That would basically limit me to this area here, right? So that's the easiest way to do it. If I were to integrate y, I'm going to integrate y, so I'm going to write dy here, and I'm going to integrate y from these two lines. So integrating between these two lines, remember this line down here is y equals negative x. So negative x to y equals, what is this line up here? Y equals 1 minus x. Okay, and then I'm going to integrate over x. So when I do dx, I'm going to integrate from 0 until we get to, remember this line here is 1, x equals 1. Okay, of x dx dy. Okay, so this is dy dx. So setting it up this way is the easiest way to solve this expected value. All right, so if I were to do this, my next step is I would go ahead and plug in for f. Okay, x. So I'd have, what is f? If I go up to the original, what is my f? F is 2/3 x plus 1. Oops. So 2/3 x plus 1 dy dx. Okay, and you could solve this. First thing you might do is pull out the 2/3. Okay, and then you end up with x squared plus x dy dx. Okay, and I'll go ahead and solve this here in a minute, but I just want to set it up both ways, like, because I said we could integrate it dy dx or we could integrate it dx dy, and we should get the same answer. Okay, so we'd go ahead and set this up, and then we would do our integral, and we would get our answer. Okay, so let me go ahead and show you how to set it up the other way. So say now I wanted to find this, and I wanted to integrate, instead of integrating dy dx, I wanted to do first thing I wanted to do is dx, and then I wanted to do dy. Okay, so this is going to be slightly harder with this support. So first, if I'm going only with if I have to think about the x values first, so how y is changing how x is changing first. So interesting thing happens here. Up top here, x is between 0 and, what's this line? This line, if it was written with regards to x, subtract or add x to both sides, subtract y from both sides. So x is going between 0 and this line, so x is going between 0 and 1 minus y. So x is going between 0 and 1 minus y. Okay, but that's only the top piece. That's only when y is up here between 0 and 1. Okay, so that's when y is between 0 and 1. So when I write y dy, that's when y is between 0 and 1. Now I need to add that to the bottom piece. So when y is between -1 and 0, what's x? X is between these two. Okay, so x is between, if I were to write this with regards to x, basically multiply both sides by negative. So x is between -y and 1. X is between -y, x, if I'm writing my dx, x is between -y and 1. And then my dy, for that second piece down there, y would be integrating from -1 to 0. -1 to 0. Okay, and then on the inside here, I would write the same thing. What was it? It's just x times fx. Okay, or xy. X times the joint distribution. Okay, and so you'd have to figure out this integral and then add it to this integral. Okay, so this is a mess, right? This involves doing your integration twice. So it's easier for this particular example to solve it dy dx than it is to solve it dx dy. But if you want to go ahead and do this, on your own time, and you could even post it to the discussion board to continue our discussion. If you want to post your answer, write it down and post it. That'd be awesome. You should get the same answer that I'm about to get when I do it dy dx. Okay, so you should get the same answer. All right, so let's go ahead and do this integration so that we can get an answer. So first, I'm going to integrate with regards to y. Okay, so if I integrate with regards to y, don't forget your 2/3 outside. Okay, so let's see, x squared y plus xy, and I still have my dx. I'm evaluating that from y equals negative x to y equals 1 minus x. Okay, let's go ahead and continue to solve this. I still have my 2/3 out front. Go ahead and throw in this integration bounds so that I get x. So I get x squared times 1 minus x. Okay, so I plugged in 1 minus x for y. Then plus x times 1 minus x. Okay, and then I need to do subtraction. Subtract it from the lower limits. I'm going to erase that there. So the lower limits, so I'd have x squared, plug in a negative x now for y, negative x plus x negative x. Okay. All right, and I still need to do my integration with regards to x. Okay, so this is 2/3 0 to 1. Go ahead and distribute this. X squared minus x cubed plus x minus x squared. Okay, go ahead and distribute this negative sign, so that negative and negative makes a positive. X cubed, that negative and negative makes a positive. X squared. Okay, I think things cancel. Hopefully they do. This one cancels with that one. This one cancels with that one. We're left with x squared and x. Okay. So x squared plus x dx. All right. Go ahead and integrate with regards to x. 1/3 x to the third power plus 1/2 x squared, 0 to 1. Okay. And go ahead and plug in 0 and 1. When you plug in 0, you just get 0. So let's just plug in 1. All right. Now I need to add these guys and simplify this. All right, so the common denominator is 6. So this would be 2/6 plus 3/6. Okay. So that'd be 5/6. Multiply straight across. 10. Actually, this simplifies a little bit. So that goes to a 1, and then that goes to a 3. Then multiply straight across. So that is 5 times over 9. 3 times 3 is 9. All right. So that is my expected value of x for this problem. And like I said, if you solve this, you should also get 5/9. And if you want to do that and post your answer, that'd be super awesome.